so for Unit 5, Day 3, we're going to be starting by talking about transformations. A transformation is any way to manipulate a figure. We have 4 types, and we're going to talk about 3 of them today and 1 of them tomorrow. Those 4 types are translation, reflection, dilation, and tomorrow we'll talk about rotation. When we talk about transformations, we are always going to start with an image, do some kind of manipulation to it, and end up with a new image. The original geometric figure we always refer to as the pre-image, and the new geometric figure is called the image. In this example to the right, we have 2 shapes. One of them has been shifted down and to the right. The original shape is labeled with capital letters on the vertices, and this is our pre-image. We would just call this A, B, C, D. Now, after my transformation occurs and we've moved down and to the right, you'll notice that the vertices of my image are labeled almost the same way, except with some apostrophes. Now, we read those as primes. So this vertex here would be called A prime. The entire image would be referred to as A prime, B prime, C prime, D prime. Let's get into our first kind of transformation. Our first kind of transformation is a translation, and a translation is literally just moving a shape around a graph. A transformation moves all points of the original figure the same distance in the same direction. In example 1, we're told to use the function to determine how the figure was translated, and we are given here what is called a transformation function. We are going to see these a lot in the next few days. Transformation functions help tell us how we get from the pre-image to the image. And now there are 2 parts to this. The first part here is our pre-image. X, Y refers to our pre-image, and it will always say X, Y. Then there's the arrow, which tells us that we're doing something to my pre-image. And after that, we're going to get a new set of coordinates for my image. So X plus 2, Y minus 3 represents the new coordinate of my image. Now let's break this down. If we think about a coordinate plane, your standard coordinate plane has an X and a Y axis. And hopefully we know that if we go up or to the right, we are moving in a positive direction. And if we are moving down or to the left, we are moving in the negative direction. And the same goes with these coordinate points in my transformation function. So if I have something that says X plus 2, I know that I must be moving in the X direction positively, which is a right movement of 2. And if I'm moving in the Y direction, a negative 3, that means I would be moving down 3. Let's take a look at what this looks like when we graph. So we are going to graph the figure and its image and determine its translation function. I'm going to start with the pre-image, EFGH. Let's start by graphing EFGH. And connect those vertices. And there's my first shape. Now from here, I'm going to take a look at what they want me to translate. This says I want to translate 2 units to the right and down 7 units. So the easiest way to do this would be for us to take each vertex, E, F, G, H, separately and move them to the right 2 and down 7 until we get a new image. So let's start with E. I'm going to count my boxes so that I know that I'm moving to the right 2 and down 7. And now this new point will be called E prime. Same thing with F and F prime. Same thing with G and G prime and H and H prime. Now, anytime we see determine the translation function or figure out what our coordinates are, there are two ways we can do it. We can do the graph first, like we just did, or we can use our transformation function, which let's write it right now, to help us find those new coordinates. Our transformation function will always start with x comma y. Then we're going to determine, well, what happens to the x and what happens to the y. If I move to the right 2 units, right and left is our x value, and I'm going to the right, so that would be a positive 2. Downwards represents our y-axis, and down is a negative 7. So our new transformation function would be x plus 2, comma, y minus 7. Now, the interesting thing is that you can write your transformation function first and get your new coordinates. So if I start with e is 0, 0, if I do plus 2 to the x, I get a 2, and minus 7 to the y, I get a negative 7. You'll see that that lines up exactly with where e prime was when we graphed it first. So that's a really good way for us to tell. Let's finish off these coordinates. And we're done. Now, the difference between examples 3 and 4 is that 4 shows the image triangle A prime, B prime, C prime. If this is the image, and we are trying to determine the coordinates of ABC, which is our pre-image, we are going to have to work backwards. It's telling me that my image was translated 5 units left and 2 units down, so I need to move the image backwards 5 to the right and 2 up. Let's do that for every vertex here. 5 to the right and 2 up is A prime, is A. 5 to the right and 2 up is B. And 5 to the right and 2 up is C. So in red, there is our pre-image. Anytime it says determine the coordinates, it just wants us to list out our new coordinates. So A is at negative 3, 0. B is at 3, 5. And C is at 2, negative 4. All right, that is it for translations. Let's take a look at our next transformation, which is a reflection. A reflection is when a figure is, you guessed it, reflected across a line of reflection. Now, those lines of reflection are very typically any horizontal or vertical lines. When we're talking about horizontal and vertical lines, the acronym that comes to mind here is HOI-VUX. We will see a lot of equations that are y equals 3, x equals negative 4, something like that, and we'll have to be able to graph those. So HOI-VUX to remember how to graph horizontal and vertical lines. We also have 3 very common reflections that we see, and their transformation functions can be memorized to kind of help us out a little bit. So reflections in a coordinate plane, specifically a reflection across the x-axis, will look something like xy, the first part of our transformation function. And to get a reflection over the x-axis, we leave everything the same except we make the y value negative. Now, if the y value is already negative, we know that 2 negatives make a positive. Reflections across the y-axis look like xy becomes negative x, positive y. So this time the x value will become negative. And then this one, if there is any one that you are going to memorize, I would recommend we memorize this last one right here, which talks about a reflection over the line y equals x. Now the line y equals x is just a regular old diagonal line with a slope of 1 and a y-intercept of 0. And its transformation function looks like xy becomes yx. The x and the y values get flipped. For every other type of reflection except for these 3, it's probably the easiest for us to just do a little bit of counting and a little bit of mental work to figure out where our new coordinates lie. And the way we're going to do that is by counting the distance between a vertex and the line of reflection, and just go the opposite side of my line of reflection, counting the same distance to end up at our new point. So for example, A is 5 away from the line of reflection. A prime should also be 5 away from our line of reflection, wherever that line may be. So in number 5, it says reflect the figure over the given lines of reflection. I'm going to start with letter A here. X equals -2 is our very first line. X equals is an example of Vux, which is a vertical line through -2. So let's draw that line of reflection through -2 here. And now I am going to flip that triangle ABC across my line of reflection so that every vertex is the same distance away from my line of reflection. So A is 1 space away from my line of reflection. So A prime will also be 1 space away from my line of reflection. Same with B. It is 4 spaces away, so B prime will be 4 spaces away. C is 5 spaces away, so C prime will also be 5 spaces away. There's our first reflection. However, now there's a second reflection in this problem. I'm now going to take that shape that I just drew and reflect it over the line of symmetry, the line of reflection, y equals 1. And I'm going to repeat that process. I'm going to flip C 1 away from my line of reflection. And now I can't say C prime because I already have C prime. So I'm going to call this C double prime. A double prime is going to go 5 away from my line of reflection. And B double prime is going to go 7 away from my line of reflection. And there's my new shape. Now for reflections across the x and y axis, there's kind of 2 ways that we can do it. We can do it exactly the same as we just did, highlighting this x axis as our line of symmetry, or this is an example where you can have that transformation function memorized. I find that having the transformation function memorized is helpful for when I'm writing my new coordinate. I know that everything stays the same except the positive versus negative of my y value gets flipped. So for A prime here, I know that my point will be at -1, -6. B prime will be found at 2, -8. And C prime will be found at 3, -2. And I can check that by graphing it. It should look correct. 3, -2. 1, -6. And 2, -8. And there's my shape. Oh, sorry, this one is in the wrong spot. -1, -6. Now the one that gets tricky is a reflection across the y equals x line. This is one where I definitely think that you should have this transformation function memorized because things get a little bit tricky when I'm talking about reflecting over a diagonal line. There's our diagonal line y equals x. Now I can do this by hand. I am able to count this. We just have to be very, very careful when we are doing so to make sure that we are not accidentally moving things in the wrong direction. So what I would do is count spaces away from my line. So C is going 1 space away from my line. So then C prime should also go 1 space away from my line. It gets a little bit tricky to see. So I like to just go with my coordinates here. And my transformation function rule says that I flip the x and the y values. So that means C prime here is going to be located at 2, 3, which is exactly what I said there as I eyeballed it. Now 2, 8 will become 8, 2 for B prime, which is here. And A prime, 6, -1 will be located right here. And that's pretty much it for reflections. And let's go on to our last one for today, which is dilation. A dilation is a similarity transformation that either enlarges or reduces a figure proportionately in size with respect to a center point and a scale factor. For our purposes, our center points will always say centered about the origin, which refers to the point 0, 0 at the middle of our graph. And a scale factor will usually be represented with the letter K. Transformation functions for dilations are pretty straightforward. We take that original pre-image, of course, once again, and to get to our image, we multiply the x and the y values by our scale factor K. So instead of xy, it will look like K times x and K times y. K values that are bigger than 1 are an enlargement, and K values that are smaller than 1 are a reduction. So if I take a look at letter A here, I'm looking at J, K, L, M. What I would do is I would list out the points J prime, K prime, L prime, and M prime. And taking our original -2, 4, I'm going to multiply each of those values by 5/2, our scale factor. 5/2 times -2, 5/2 times 4, leaves me with the new point, -5, 10. And that's just for J prime. Let's plot this first. JKLM will end up at -2, 4, -2, -2, -4, -2, and -4, +2. So now I'm going to take J prime and put it at -5, 10. And I will repeat for all my other values. So -2, -2 times 5/2 is -5, -5. L prime will be at -10, -5. And M prime will be located at -10, 5. Okay, perfect. And that is how we do dilations.